have to take the first step further on out there. We have to move on and realize that means and mews are not the only thing that will hit us in our life as engineers. Sometimes there are other features of the system we're looking at, we're facing, than the mean that might be our main focus, our main interest. And here's a little example to motivate the talk about standard deviations and variances, because the height example might not be the best one to motivate that one. However, when you produce stuff, for instance, at Lundbeck, producing tablets, and I assure you they have machines out there that produces those little white things that they throw out in the glasses to us. It comes typically from a big what's the name of a big thing? In beholder, in Danish. What's the English word for beholder? Container, thank you. A big container of powder, and then gets taken out into the tablets. And I'm not so much of a production engineer myself, as you can hear, but I've seen it done, and I can follow the principle. I'm sure you can also. It's important when you produce anything, of course, but now we use the tablet example. It's important not only that the tablets on average hits the target with the amount of active substance. They claim they have 0.1 milligram per gram active substance in the tablet. It's very important that on average the tablets have what we claim they have, and it's important that each of them have it. They should not be allowed to vary a lot, right? Tablets should be the same. All of them should have the same amount. The variability should be small, right? It's very important. There is a very, very high price to pay if Lundbeck does not have their production in control such that they can produce individual tablets that when you start checking them comes with a very, 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 very low variance. And of course they have to specify what variance they can produce with, and if they don't live up to it, they'll get into problem. Of course, people will either die from overdose, or they will, worst case, die because they are not treated if it's underdosed, right? So of course, I hope you see the point. It's very important to be on top of the variance in such a production system. That is just to let us know it can be very important to think about the variance itself. Of course, the mu is also important for the production of the tablets. It should be on the right target, but damn it, the variance must also be okay, right? So sometimes the variance is very important in itself. The variance, I have told you that already. The variance itself is when we compute it, when we compute the sample variance, because we know that. I told you that already 3 weeks ago, how to compute a sample variance. That's not anything new here. Compute the variance, I told you, fine. But think about how good it is as an estimate of the true variability of my production process, right? When I compute a variance on 10 tablets, 20 tablets, how good an estimate, how true is it? How close to the real production variability is my sample variance? That's the question we should ask ourselves to make that point. Then we have to think about how can a variance be different from time to time? What is the distribution that would describe my problem with my variance? My variance becomes a different thing from time to time. My variance estimate is a random variable. This is an abstraction level I struggled with myself 31 years ago. The first time someone told me the variance has a variance, I'm fucking gonna find something else to study than this stupid statistics. But hey, if you think about it, it makes sense. Just because I was pretty stupid, you don't have to be. It's pretty obvious if you think about it, that if I compute my variance today and I compute it again tomorrow in the same production process going on, I take 10 samples today, I take 10 control samples tomorrow, of course the two variances I get will be different from time to time. It's pretty obvious if you think about it. But hey, I studied at university, so nothing was obvious to me. But you're engineers, so I'm sure it's obvious to you. We have to think about how can it be different from time to time. Hey, this is where we should consult the guys knowing about the math and the probability theory. Because how can a variance, that's a pretty complicated function actually, if you think about it. A variance is the square of something which might be normal or might have something else, but let's assume it's normal. And I square it, and then even the standard deviation, I root it again maybe. How can we find the distribution of such a thing? Well, we can. And if you'd like to know a little bit about the math, I have some extra math stuff for you with a little bit of the proof, but the proofs of these things are not part of the core of this course. We accept it. Here is what we should accept. That variances, sample variances, behaves like something which is called chi-square distributions. This is a new distribution popping up to us again here. Actually, theoretically, chi-square distributions pops up as the square of normal distributions. If you square a normal, you get a chi-square distribution. This is the first time we meet it. The chi-square distribution is a positive thing, right? A variance is positive, it makes sense. It's a right-skewed distribution. It exists in R. Here I use the density function of the chi-square just to plot it. Otherwise, we don't really use the density a lot for what we do, as we discussed last time. But we use the density functions to show. And here comes the consequence of this theoretical results. Here comes the explicit formulas that you can use, that I used on my slide 1 some minutes, a couple of hours ago. When we construct the confidence interval, first we construct it for the variance based on the chi-square distribution. We have a chi-square distribution. It should be the right chi-square distribution because it also depends on the number of observations. There are different versions of the chi-square distribution, not only one of them, but many different ones are out there. We should choose the right one. And the right one is named the one with n-1 degrees of freedom. Take those words as just a name for the right distribution for us now. I didn't try to explain you why we call it like that. There is a reason for it, but I didn't even try to give that to you now. We can get back to that, but not now. Just take it as this is the right chi-square distribution to use when I'm going to quantify the uncertainty of a variance based on n observations. I use the chi-square distribution with the name chi-square with n-1 degrees of freedom. That's the right one for me to use because the theory tells me that's how it works. Right? I don't prove the theory to you. And the way we use it is just to use our computed variance twice. Now this is not additively like before, now it's multiplicatively actually, the way it works. So we divide, this is the chi-square, for instance, 0.975, and this is the chi-square, 0.025, and then we have 95% in here. It's not symmetric, but it's symmetric in the probabilities, but not in the quantiles, you could say. Right? If I take the large one and divide by here, and the small one and divide by there, so I look up these quantiles. Sorry. Not emotions, just spit. Saliva. It's good that we are soon done now for today, otherwise it gets to a point where I'm having it. I have a long list on the soon fires thing there. Yeah. Let's try to postpone it as much as we can. We look up those quantiles, and we do that by R, of course. We can just root everything. Can you see that? The same formula with the square root. And then I get the confidence interval for the standard deviation. Here it goes. Data. I have a mean. I have a computed variance. How do I get the confidence interval? I look up the right quantiles in the right. With 20 observations, I use DF19. They are around 9 and 33. That's how the chi-square works. And the confidence interval becomes like this, right? So it's straightforward use of the formula I just showed you by finding the right quantiles from this new distribution that I've shared with you using R, right? And you cannot solve this without using R. That's the thing. In the old days, if you look at old statistics books, or not only old ones, but all of those, not as nice and modern as our ones, you will see a lot of tables in the back of statistic books, normal tables, T tables, and chi-square tables, and F tables. We meet that later on. But hey, it's a pretty old-fashioned thing to look around in tables when everything is on our computer or smartphone or anything. So we use R. Those distributions are everywhere. They're in Excel, they're in Maple, they are in all sorts of software. This is just the other example. So let's not that's the heights example. That's the one I showed you on slide 1. We had 10 heights. 9 degrees of freedom would be the name for the right chi-square distribution. I say Q chi-square with the right number there. I ask for both the 2.5 and 97.5. I do it in one step. I get both of them. The 2.7, the 19. I plug the 19 and the 2.7 into the formula I just showed you, and I get the result of slide 1 saying that based on 10 observations, my interval for what is the variability of heights among people, well, it's somewhere between 8 and 22 centimeters. That's a pretty wide interval, right? This tells us that it's more expensive to be precise on the variance than it is to be precise on the mean. Precision on the mean comes cheaper than precision on the variance. N, the size of N is money out there, right? For Lundberg, it's how big a study should I make to test that I'm okay, right? So N is money. So this is a recap of slide 1, where I gave you the 2 new intervals, the 2 new methods, your first real statistical, inferential statistical methods of the course, with the confidence interval being a very generic one. We're not done. How did you do, those who played with me? Well, as another old guy, Meatloaf, says, 2 out of 3 ain't bad. The tails of the T distribution is always heavier than the standard normal distribution. I asked you, what if Z is a standard normal and T is a T-distributed one? The 15 actually doesn't really matter, whether it's 9 or 15 or a million, I don't care. Would the probability of being beyond 2 be larger in the standard normal than in the T? No, that's the wrong way to put it. It's the opposite, right? So the answer was false. 2 out of 3 is not bad. Do we have time just for a little more play? I'll give you 1 minute here. The question is, the T distribution is generally very different from the standard normal. Is that true or is that false? We could also make a raise hand in here. That's what we did in the old days. Sometimes we forget to talk and we sit around the table and SMS each other. So maybe I should just ask out in the room. Who thinks that the T distribution is generally very different from the standard normal? Is that true? Raise your A hand if you think that's true. Now it's good to be on the back row because you can just check out what's going on and then, yeah. Who thinks it's false? Let's see. And who doesn't fucking care? No one. Good. Of course, it's very much the same, but I also, as I put here, you can say it's very much the same, not a difference. But we should be a little bit careful in the end. And if the n is not very large, right? Down n, 10, 15, so it's good that you were a bit worried. I appreciate that. You should actually, apart from those more or less being the same, there is a reason to use it for a small, expensive data setting. It can be important. I have one more question for you. The normal distribution can often be used to do statistics, no matter what the distribution of the actual phenomenon is. Who thinks that is true? Who believes this is false? How did you do? Thank you. And then the concern at the end, yes, the normal can be used always. That's the sloppy version of it. When we want to make the one-liner commercial for the normal and for the tools, we would say, whoa, it can be used for everything. But with everything, there is a catch, there is an assumption, there is a condition, at least if the n is large enough. And then I'd like you to start thinking about how the heck do we then know whether n is large enough? It is not enough to get a paper accepted in Lancet, for instance, or I'm sure it's not enough at Novo Nordisk top management level that your argument for saying that it's okay to use my normal-based data because my stats teacher, he told me the rule of thumb was n equal 30. I'm sure that top management of Novo Nordisk is pretty not interested in what your stats teacher told you as a rule of thumb. He wants to know for sure, is it okay or not? The rule of thumbs are not good enough. In our course, it's good enough because we cannot solve everything in a 5-point course. But that's a difficult challenge, actually. I'm not asking you to solve it now, but don't worry about it too much. Be happy and do today's exercises based on the assumption that everything is okay, right? So enjoy it and see you over there.